Welcome back everyone, Patrick here, and moving on to the next question, we have to show that a triangle with these three vertices, -4 and 0, 9 and 1, and -1 and -5, is a right triangle. Now there's actually two different ways to do this. The more common way is actually the longer way as well, so I'm going to start off with that, and then I'll show you a shorter way at the end. First thing I'm going to do is I'm actually going to draw just a rough diagram of this. Usually when you draw even a rough diagram given coordinates, you can kind of see where the right angle is going to be. So -4 and 0 would be like over here. Let's actually label these. This is A, B, and C. So this here would be point A. And then we got B, which is 9 and 1, so that would be like over here. So that's point B. And then we have -1, -5, and that would be like down here. And that's point C. Right, so you could kind of tell, if we draw a triangle here, if there is going to be a right angle, where is it going to be? Most likely over here. So the more common way to show this, that this is a right triangle, is we can find the lengths of all three sides. And then remember, with a right triangle, Pythagoras' theorem has to hold. A squared plus B squared equals C squared, where this C is the length of the hypotenuse. So if we could find all the lengths and then show that the Pythagoras theorem holds, then we prove that it's a right triangle. So let's first find the length of AB. And what is the length formula just in general? Between 2 points, if you remember, it's the square root of x2 minus x1 squared plus y2 minus y1 squared, where the 2 points are x1, y1. That's a comma right there. And then x2 and y2. So given 2 points, the length between them is this formula here, or the distance between them. So if we're working with AB, we can just label, let's do x2, y2. This would be x1, y1. So we would have the square root of x2 minus x1. So it would be 9 minus -4 squared plus y2 minus y1 squared. So we would end up having, this would be 13 squared plus 1 squared, which would be 169 plus 1, which would be 170. And let's leave it as the square root of 170. Let's leave it as an exact value. So that's the length of this line right here. And now let's do the same thing for AC. So this is AB here. So between A and C, so between these points, we'd have what? -5 minus 0, which would just be -5 to the power 2, plus -1 minus -4. Give me a sec here. Yeah. -1 minus -4. And that would be squared. So we would end up with what here? This would be 25. -5 to the power 2 is 25. -1 plus 4, right? These two negatives turn into a positive. -1 plus 4 would give us 3. 3 squared would be 9. So this would be the square root of 34. So that would be the length of AC. And then we could find the length of BC. It would be the square root of 9 minus -1, which would be 10 squared, plus 1 minus -5, which would be like 1 plus 5, which would be 6 squared. And this would be 100 plus 36, so the square root of 136. So that would be BC. So if we label these, over here, we would have square root of 170, that's the length of this line. AC is the square root of 34, and then BC is the square root of 136. Those are the lengths that we found. And let's see if this is going to hold, if the left side would equal the right side with the Pythagoras theorem. So what we would do, we would have a squared plus b squared equals c squared. This a, b, and c is different than this a, b, and c, by the way. So remember, the c is the hypotenuse, the length of the hypotenuse, which is the square root of 170. That's why a diagram like this would help, but we could also tell that square root of 170 is greater than the square root of 34, square root of 136, right? It's the larger side. So we know that's going to be the c. So that would be the square root of 170 squared. And then it doesn't matter which one is a or b between these two. So we'll have the square root of 34 squared plus the square root of 136 squared. Notice the square roots would go away, right? The square root of 34 squared is just 34. And then over here, square root goes away. And then notice that indeed 34 plus 136 does give us 170. And so because the left side equals the right side, the Pythagoras theorem holds with these three lengths, which means that these three vertices do give a right triangle. Another way you could prove this is notice that from this diagram, usually a diagram would help here, notice that this has to be 90 degrees. And so notice that these two slopes have to be perpendicular to each other. So this is an extra check you could do. Now, if you get this on a test, your teacher is most likely going to want to see the method that I just showed. But you could quickly test it as well. What we can do is we could find the slope of this line, AC, which would be what? y2 minus y1 over x2 minus x1. So we would do y2 minus y1, so negative 5 minus 0, over x2 minus x1, so negative 1 minus negative 4. And notice we would get negative 5 over 3. Right? That's the slope of AC, and it makes sense. Notice it's a downward slope. And then we could find the slope of BC, which would be y2 minus y1, so negative 5 minus 1, over x2 minus x1, so negative 1 minus 9, which would give us negative 6 over negative 10, which would give us positive 3 over 5. So that would be the slope of BC. And notice that if there's a 90 degrees between them, they got to be perpendicular. And notice that the slopes are perpendicular because they're negative reciprocals of one another. Right? This slope, if there's 90 degrees between them, they're perpendicular, meaning the slopes are negative reciprocals of one another. And we just showed that over here. So that's another quick way that you can